In 1959, Aronoff and Bohm predicted their now famous namesake effect. To some extent, the explanation of this effect is obvious. If we consider an electron beam when it passes through a magnetic field, it is deflected by the Lorentz force. Quantum mechanics, being a more general theory, predicts the same deflection as well. The quantum explanation of this deflection is based upon phase shifts of the quantum mechanical wave caused by the vector potential. Thus, for the AB effect, one might expect if the magnetic field is turned off, the deflection and the phase shifts disappear. The remarkable and defining subtlety that Aronoff and Bohm pointed out is that such a phase shift can occur in situations without any deflection or force. So, we have come to believe that sometimes things can happen without a force. As soon as we know that, it is natural to look for other examples of this remarkable behavior. The magnetic and electric AB effect and their duals are examples, while also the Matteucci Pozzi effect was reported in Physical Review letters in 1985 as an AB effect. However, theoretical physicist Timothy Boyer challenged this view in 1987 for the MP effect, and again for both the original magnetic AB and MP effect in 2002. He predicted the presence of force for both scenarios. A physics research group at the University of Nebraska-Lincoln decided to look at the presence or absence of a force for the MP effect. Is or is it not one of these rare AB effects?
The field from a charged wire falls off with distance. However, the interaction time increases the further you are from the wire. These two contributions cancel each other out, so we end up with no deflection. Thus, one wire attracts the electron while the other repulses, but the net effect is no deflection. Given we weren't expecting a deflection, we were, however, looking to see the electron arrive at the detector with a time delay. To that end, we made short electron pulses by hitting a piece of metal with the pulse laser, and we looked at the arrival time of the electron for different voltages on the wire. In this case, we were expecting that Professor Boyer had the correct predictions. But given the complexity of a real experiment, you never know what's going to happen. So we were very surprised to find that the delay matched the prediction nicely.
So for the question that there are really no AB effects, I would say no, not at all. We did an experiment in 2007 where an electron passing by a solenoid did not experience a force. This confirmed for the first time that the original magnetic AB effect is very special. Still, it's puzzling that Boyer's argument fails for one experiment and works for the other. The reason is that we think the assumption made by Boyer that Newton's third law holds is not correct. Newton's third law is generally valid in the sense that it expresses momentum conservation for closed systems. But for the two mechanical parts of the AB system, that is, the electron and the solenoid, Newton's law likely does not hold. Momentum can be stored in the third part of the system, the electromagnetic field. If this happens for the AB effect but not for the MP effect, then the experiments can be understood.
Yeah, at first sight it would appear so, because force, right, mixing classical concept with quantum mechanical concept, phase, is not generally a good thing to do. However, Professor Zeilinger in the late 80s made a study that showed that the Aronoff-Bohm effect is dispersionless. That's the crux of the matter. That means that if you consider a wave packet, then if the phase is velocity dependent, then there is dispersion. In classical mechanics, that would mean that you would observe or that you would predict a time delay. However, if there is no velocity dependence for phase, then the effect is dispersionless. And that's a very special feature, and of course we should note that an experiment demonstrating that feature has never been done. Yeah, the earlier measurements on the absence of force may be sufficient, but that is not quite certain, simply because we do not know if the macroscopic, the description of physics at the macroscopic scale and the microscopic scale, if they are the same. If they are the same, then the experiment is sufficient. But in the end, we also need to establish that experimentally.